Hey students, in this video we're going to be talking about chemical bonding and what are alkanes here. So to start off, we are going to look at the name of this general field, which is called organic chemistry. If you've heard of that, it might have been from a friend or a sibling or someone who's taking a lot of science classes. You might take organic chemistry, particularly if you're going to some sort of medical field, or a dentist or a doctor or someone else in the medical field. So organic chemistry really is just a branch of chemistry that is specifically focused on hydrocarbons and things that are related to hydrocarbons. So it's a branch of chem focusing on hydrocarbons and their derivatives. These are like things that are built off of the basic structure of a hydrocarbon. So all hydrocarbons are essentially just hydrogen and carbon bonded together. In hydrocarbons, you have a main carbon chain, we call it. This is the, or the parent chain. This is a carbon, or these are carbon atoms joined to form a backbone. We sometimes call this also the parent chain. So how are atoms of carbons and other elements held together in these compounds? Well, this is particularly chemical bonding. Now, the question is, do you remember what kind of bonding we're talking about with particularly carbons? Well, when we're talking about bonding anything, we have to look at the electrons. The electrons are the ones that are going to be shared or taken, and so we have to know a little bit about the element and how many electrons it has, and therefore how many it needs to fill its outer electron shell or its valence shell. So the electron shells, again, if this is a review, then great. If you remember this, awesome. Electron shells are the areas of the atom that hold electrons. Okay, and different shells hold different numbers of electrons. If you recall, the 2, 8, 8. All right, example here. Again, this should be somewhat review. So when we're talking about carbons and hydrogens specifically, we're really talking about the sharing, which is a covalent bond, the sharing of two or a pair of valence electrons. Okay, in particular, it's two between two atoms. And the goal ultimately is to fill the outer valence shell of electrons. So, for example, hydrogen, if you look at the periodic table, hydrogen is all the way up to the top left. It has one electron there. If you have one electron there and it's in its first shell, it's trying to fill its first shell, and the first shell only holds two. So it only needs one more electron to feel like it's filling its electron shell. So therefore, it only bonds with one of the things. That's why we find hydrogen often as H2 as a example. Conversely, we have oxygen. Oxygen is missing 2 electrons to fill its outer electron shell, which holds 8. It has a total of 6 in its outer valence electron shell, and so it wants to share 2, so it'll actually make a double bond, as you can see here. And often we have O2 as an example. Nitrogen is missing 3, and therefore it bonds with itself. It makes a triple bond, and so we often see nitrogen gas. It's actually the most prevalent gas in the atmosphere. So this is just an example of some atoms that are covalently bonded. And if we were to draw this in a different way, in a particulate view, where these are the atoms here, right? And we have 2 atoms bonded together here. This would be like hydrogen and hydrogen bonding together, and it would become, you're doing the electron dot structure, or the Lewis dot structure, it would be like that, where these dots are the valence electrons. Again, this should be somewhat review for you. It's been a while though, so it's good to look it over one more time. Okay, so the next step is we have to be able to figure out how to show this, this bonding, particularly when we're doing hydrocarbons, which has a lot of bonds on them. And we have actually 4 different kinds of ways that we typically see these molecules. These are not the only ways, but these are the ones that we're going to be seeing often in this particular class. So, so the first one is electron dot formulas. These actually show valence electrons. And an example of this is a particular compound called propane, okay, where we show the electrons in the center, or the carbon chain or parent chain, as dots. Again, they're being shared. Now, carbon needs to have a total of 8 valence electrons. And right now it just has 1 pair right here. So it needs to have 3 more pairs, or 6 total electrons. It has 4, and the way it satisfies its 8 total is by surrounding itself with hydrogens. We call that saturating it. All right. So again, this is an example. It's called propane. If you recall, pro or prop is the prefix for 3, and ane is the prefix for alkanes. So again, this is an electron dot formula. It shows the electrons, the valence electrons. And again, it's really important when you're looking at filling the outer shell of valence electrons to make sure that you are. The structural formula is something that's also pretty popular. It's more popular than the electron dot formulas. You'll see them more often. And this is, again, instead of you having the dots, you're going to represent the electrons as lines. So show valence electrons as dots. This is going to show a pair of valence electrons as a stick or a line. So whereas you see over here with the carbon you have dots, we're going to redraw this. So carbons are now going to have a line, and these lines again represent the pair of electrons being shared. And then again, each pair is going to be represented as a line. When you look at a line on a structural formula, you want to remember that that line represents a sharing or covalent bond between two electrons, two valence electrons. And that's how we draw the structural formula. Now the molecular formula, it specifies specifically the number of atoms of each element. This is the most simplified way of drawing the molecule. And this example would be C3, there's 3 hydrogens, H8. This is the molecular formula. What this does is it's obviously much faster to write this and draw this. However, you're missing a lot of the structure. And also, this doesn't show you whether or not it's an isomer. Isomers have the same molecular formula, but different structures. So it can be helpful for saving time and um, um, for showing a molecule that is very complex, for example, that has a lot of atoms. You can simplify it this way. However, you do miss the ability to have a more detailed conversation about structure. Condensed formulas are kind of a combination of molecular and structural. Condensed formulas show molecular formula show um, a condensed structure. Okay, so this is the example. You would have, instead of having this as all the atoms, right? The structural formula is all the atoms here. You combine this part right here into a condensed or a molecular formula. So that part would become CH3, and then that's bonded with a CH2 in the middle. And then on the right-hand side, you have CH3 again. Okay, so that's the condensed formula. Again, all of these represent propane, the same thing, but they're just drawn in different ways. So alkanes are a little bit different, or specific rather, for how we draw them and what they are and what's included in them. Alkanes are hydrocarbons, a particular kind of hydrocarbon, and they have single bonds between the carbon atoms. The most simple formula or simple alkane is CH4. It's a single carbon, and we call this methane. This is methane. This is a particular shape called a tetrahedron. If you notice in this picture here, the tetrahedron really describes the sides, if you will. It's sort of a pyramid-shaped structure. And this angle right here is a very specific angle. This is 109.5 degrees. It always is that case. And it's good to know the structure of a molecule. These angles are always 109.5. Sometimes it's drawn like that as well. And then we have our second smallest alkene, which is ethane. It's C2H6, and propene, C3H8. So, question for you, can you figure out a formula for figuring out how many hydrogens an alkane has if you have n number of carbons. So my question is really this: you have Cn, n representing a variable number of carbons, how many hydrogens would you have? Well, look at the pattern that you noticed with methane, ethane, and propane. CH4, C2H6, C3H8. What you should notice is that in order to figure out the number of hydrogens, you take the number of carbons, you multiply it by 2, and you add 2. This is the formula for figuring out the number of hydrogens and carbons from the number of carbons. We have a lot of uses for alkanes. Rather than just talking about the chemistry of it, we should talk about what it's actually used for in the real world. And methane is used as natural gas. This is the main component in natural gas. A lot of us living near city centers have natural gas or methane. Ethane is actually used as a catalyst. It actually helps to speed up reactions, all sorts of chemical reactions. Propane is used as a fuel for like cooking. And heating. Some houses are heated by it. Butane, again, is also used as a fuel. Again, but more for smaller lighters. And then pentane is used actually for the production of plastics. Right, these are just some of the different uses of alkanes. And as we get larger and larger, we have different uses. All right, so we just went up to butane and pentane. It's really important for you to memorize the prefixes meth, eth, prop, but, pent, hex, hept, oct, non, and dec. These are all of the prefixes that indicate how many carbons that particular molecule has. As you can see, there's examples of the molecular formula and the condensed formula. Again, two of the examples of types of ways in which we can represent the molecules. What you should also notice is as you get larger in terms of the number of carbons, the boiling point changes. How does it change? Well, it increases. So the larger the molecule, the harder it is for the molecule to boil. Or another way of saying that is the more energy it takes to boil that particular molecule. All right, so name and give the molecular formula for the alkane with the molar mass of 44 grams per mole. Well, so this is an example here, and so for 44 grams per mole, you would say, well, if carbon is 12 grams per mole and hydrogen is roughly 1 gram per mole, well, which hydrocarbon would be, or alkane would be 44? Well, you have to play around with it a little bit, but hopefully you see that if you have, um, let's see, if you have 3 carbons, 3 times 12, okay, that would be 36. Now, if I have 3 carbons, I would have times 2 plus 2 would be 8 hydrogens. 8 times 1. Well, if I take 36 and 8 and I add them up, I get 44 grams per mole. So the answer to the first one is propane. Okay. Try figuring out what the next one is. 72 grams per mole. And another challenge question for you is write the molecular, condensed, and structural formula and electron dot formula for a 7-carbon alkane. And the last one is if an alkane has 497 carbons, then what would be the molecular formula? All right. So that's it for chemical bonding and for alkanes.